So today's lecture is the 10th lecture that's regarding the information channels. So until now we studied about the source encoding schemes, and today as well as the few more lectures that follows where we'll be studying about information channel. So more information here, I mean regarding the information channel, or this is a communication channel in other words. So this is the picture or the figure that represents the overall communication setting. So here we have the signal, I mean source, that emits different informations, maybe alphabets or digits or any other information like a voice signal, video signal, and so on. And then we do the analog to digital conversion. So basically here, after this block, we have the digital representation of the original signal here, if it was not actually digital. Now here it becomes digital after sampling and quantization, all those, or in general, analog to digital conversion. These bits here, because this is digital, we have bits, right? So that is the input for the source coding block. So all these days we studied regarding the source encoding scheme. That means we have different data bits. We want to represent that data bits or set of information in an efficient way. That's why we use the source coding. We use some algorithms like Shannon-Fano coding or Huffman coding, where we represented the data as a I mean, in a different way. I mean, every symbol was represented by different number of bits. Instead of transmitting every symbol using the same number of bits as done in ASCII. ASCII is also a kind of coding scheme, but it's not so intelligent. Maybe Huffman coding is much intelligent than that. So we have studied regarding all that, like Shannon-Fano coding or Huffman coding. Those concepts will come under this block. That means this step, source coding. We have, in case of source coding, what do we have? Input. We have some input symbols, and we try to represent, or we try to code those information in an intelligent way, so that we do not have to transmit all the data that comes into the source coding block. We just represent or transmit only few bits, right? In case of Huffman coding, you have seen we use the few number of bits to represent the code for a symbol that is very frequent, and we use a longer code for a symbol that is not so frequent, right? So we have reduced all the redundancy here in case of source coding using different source coding technique. And then the next step is channel coding. So in case of channel coding, we will be using few more algorithms that we will study in the maybe in the 4th module as well as in the 5th module, that will talk about the channel coding schemes, different algorithms. So what's the story in case of channel coding? In case of channel coding, we will be targeting mainly the errors or the noise that is introduced by the channel. So the data that comes, or the code that comes after the source coding into the channel coding block, will be represented with some redundancy bits. Okay, so why do we add redundancy in the channel coding step? Because there is a chance that when the data enters into the channel here, the yellow color is the channel, so the data may be spoiled or altered by the channel because there is noise added in the channel. That's why we will add some extra bits in the channel coding. So even if there is noise in the channel, those extra bits we can sacrifice so that we will have what is required at the receiver. So that's why we use the channel coding scheme. So channel coding scheme, the overall summary here is it will add some redundancy to the data that comes into it, and it is sent to the channel. So here this all yellow color is a channel, but also there are some blocks here, like at this point here we have a modulator or digital to analog converter. At the receiver side again we have one more block, that is demodulator, analog digital converter. So this is digital to analog and this is analog to digital. Okay, so this is also considered as a part of the channel in this figure. But these two blocks, that is a modulator as well as demodulator, can be separated from this yellow block. Right? Okay, I mean it can be separated from the channel. So in this block, it is shown together, no problem. Okay, so finally, after channel coding, data comes to the modulator, where the digital data, the bit stream, what comes here, is converted into analog D to A. And then it is transmitted. So here, this part is totally the channel. So this channel may be a wired channel or a wireless channel. For example, in case wired transmission, such as coaxial cable or fiber optics or a twisted pair cable, that's what we use to connect the computers, a LAN cable. So all those cases, it's a wired transmission. Otherwise, we have wireless transmission, where the free air is the medium or the channel to carry the data. So during that time, what happens here? There is a chance of noise. So for this channel, that is yellow color here, there are two inputs. One is the data, that is what you want to transmit, plus the noise that is added from the surrounding. Maybe in case of a wired channel, from where it is added. Maybe some variation in the electric pulses that causes noise. In case of wireless channel, where is the noise? Because it's a free medium, free air. The property of the air or the channel, what you call, it varies with respect to time. Or maybe there are some obstacles along the path that causes some destruction to the propagation of the signal. So all that contributes to the noise. Okay, so that is also an input for the channel. And then, of course, from the channel, the data comes to the receiver side. So this is altogether is the transmitter here, the upper blocks. And the lower blocks here, this is the receiver part. So at the receiver, that is, data comes from the transmitter to the channel, from the channel to the receiver side. So at the receiver side, what do we have? We have the demodulator that will convert the analog signal into digital. And then we have the channel decoder, where we will try to adjust the errors. For example, at the transmitter side, we did the channel coding. So the reverse process here is a channel decoding. I mean, we have the decoding algorithms here that will address the issues caused by the channel. And then we have the source decoder. So it will do the reverse process of source encoding. So in the source encoding, if you remember, for example, Huffman coding, we have represented the data with less number of bits, right? We did not use the same number of bits for every symbol. But we want to get back that. What was the actual symbol that is transmitted? We want to read that. So source decoder has some algorithms that will help the receiver in understanding what the source coding or source encoding has done. Source encoding has represented every symbol by different number of bits or different representation of the bits. For example, A, B, C were the initial symbols here. Now A is represented as 0, 0, B is represented as 1, 1, 1, 1, C is represented as 0, 1, and so on. Now, the source decoder will try to understand if it is 0, 0, it means it is A, or it's 1, 1, 1, 1, that means it is B. So it will give back the original signal here. Actually, that is reconstructed here. And finally, we get the information that was originally transmitted. So again, it is digital to analog conversion here. So here at the transmitter, analog to digital conversion; at the receiver, the reverse process, digital to analog conversion. So this is the overall scenario of a digital communication system. So the summary here is we have a transmitter and a receiver, and another component is the channel. So channel is the medium through which the data propagates from the transmitter to the receiver. Okay. At the transmitter, we have different sections, such as source encoding, where the data is represented efficiently using efficient number of bits or using some intelligent scheme to represent the data, but to reduce the redundancy. And in case of channel coding, we add some redundancy into the data that comes in so that any errors that are introduced at the channel can be solved at the receiver. Those errors can be addressed at the receiver. Okay, so and then the third block here is the modulator. So modulator will modulate this data, that is a digital data, into analog waveforms. We have different modulation schemes, digital modulation schemes, like amplitude modulation or frequency shift keying, ASK, FSK, that's what we call different modulation schemes. One will operate on the amplitude, other may operate on the frequency, other may operate on the phase, that is PSK, phase shift keying, and so on. So anyway, through different modulation schemes, the data is transmitted and through the channel. So all the data that comes to the channel will be analog pattern, a continuous electrical signal. And at the receiver, we do all the reverse process that was done at the corresponding block of the transmitter. For example, at the demodulator, we do the reverse process of the modulator. That is, we try to demodulate. So basically converting to digital back. And then at the channel decoder, we do the opposite process of channel encoding. Okay? We will remove the redundancy here. The redundancy was added at the channel coding. Here we will remove that redundancy. And at the source decoder, we will try to understand what the data was transmitted, because here we represented every symbol as a data bit. Now we will try to understand if it is a data bit, then what would be the symbol. Okay, actually we will reconstruct that finally at the reconstruction here, that is digital to analog conversion. And we will get back the decoded signal. So in today's discussion, as well as few more days, we will be discussing regarding this channel, because in the next slide, I will tell you the different points, what happens in the channel. Because when the data is transmitted from the transmitter to the receiver, it has to propagate through the channel. So channel will introduce some noise. So the data may get spoiled during their transmission. So we need to take some extra care when we talk about the channel. So suppose if you transmit A, there is no guarantee that you will receive A here. It may become something else. You transmit 0, 0 here, then there is no guarantee that you will receive 0, 0 here. Maybe you will receive 0, 1 instead of 0, 0. So we will use some schemes here, or some properties we will try to understand, so that how can we decode what we transmitted. So that study, some statistical study to understand the behavior of the channel, that we will do in today's lecture, as well as in few more lectures. So right now I will list some of the properties of the channel. So first one, channel is a discrete memoryless channel, we call it as. So the word, discrete, that means we have finite set of symbols. Okay, it is not continuous symbols. We have finite set. And memoryless channel. Memoryless channel. Why do we use the word memoryless? Because every symbol into this channel is independent. It does not depend on the previous symbol. Previously, the source emitted A. The next symbol, what is the next symbol? I don't know. Maybe A or B or C, anything possible. It is not dependent on the previous symbol. So it is a discrete memoryless channel. So more information here. Input is a discrete symbols. For example, can you give me some example, discrete symbols? Yeah, all the examples what we considered previously, for example, different sources emitting different alphabets or other symbols, etc. Tossing the coin, all these are discrete symbols, because we have finite set of symbols generated by the source. For example, if you consider alphabets, there are 26. Tossing the coin, there are 2. or throwing the die, there are 6 possibilities, and so on. And the output of this channel is also discrete symbols, because we will be trying to understand what was transmitted. So if you transmit some alphabets, and I say, then what is your output? Output should be one of those letters from the alphabet list, right? Out of 26, you should be getting some alphabet. Or if you're tossing the coin, 2 possibilities, either head or tail you should be getting. I don't know what I did. Maybe I tossed the head and you get a head, or you get a tail. Only 2 possibilities. I mean, we have only limited number of possibilities. So that's the discrete symbols. Output is also a discrete symbol. So and also these symbols are independent. Anything can happen in the next subsequent attempts or subsequent transmissions. So that's why the channel is discrete memoryless channel. And the communication channel provides the electrical connection between the transmitter and receiver. So why do we call it as electrical connection? Because the channel connects the transmitter and receiver, right? Channel is in between the transmitter and receiver. That's what we have seen in the previous slide. And it's electrical connection, because we will be transmitting some modulated signal through the channel. That's the analog signal, right? That's the electrical thing, having a phase variation or having some amplitude variation or frequency variation and so on, or maybe all together. The channel causes several impairments. I told you that channel has 2 inputs. One is the information that you want to transmit. The other one is what? Other one is the noise. Okay, so here, what are the different impairments, or what are the reasons? Some are due to amplitude and frequency response variations of the channel. Okay, the channels, for example, if you consider the wired channel or a wireless channel, maybe in a wired channel there may be some glitch in the channel. The amplitude of the signal transmitted may suddenly change at some moment, or the frequency. Or if you consider a wireless channel, of course the property of the channel, I mean free air, changes with respect to time, because maybe the weather changes, or more density variation, or many reasons. There exist many reasons for the change in the behavior of the wireless channel. Maybe more fog, or more dust in the dust particle in the air. All this contributes to the change in the behavior of the channel. So all this amplitude and frequency may change. And but the input and output are analog, even in the digital system. So what we have seen in the previous figure was the digital system. But I told you that the input and output are analog. You see the modulator and demodulator, right? So when we modulate, even though it was, maybe I should go back to show you here, modulator here. So even though it was digital, finally when it is transmitted, it's converted into analog, right? So finally we want the representation to be in analog. So input or output are analog, even if it is a digital transmission. Then why do we use digital transmission? Because if you know the digital, when you represent the data digitally, there are several benefits, more flexibility. So we represent it in digital scheme, but finally we will be interpreting as analog, the data as analog, maybe input or output. Okay. The other channel impairments are due to the variation of channel characteristics. This is what I mentioned mainly in a wireless channel. This is very common. Even in a wired channel, it happens. Channel characteristics vary. Next, all of these results in what? Channel modifying the input signal in a deterministic way. That means you want to transmit a 0, but channel is not ideal. Channel will try to spoil your transmission because of some noise added. As a result, channel modify the input signal, and you wanted to transmit a 0, now this has become like 1, or maybe 0 also. If you are fortunate, it remains as 0 itself, or it may become 1, something else. So it may be a deterministic way or indeterministic way. We don't know. Sometimes we can predict what would be the output, deterministic. Sometimes we cannot predict what shall be the output. If I say I want to transmit alphabets, I don't know which alphabet I'm transmitting, and the output is something else. There are 26 possibilities what you transmitted, right? What you receive, also there are so many possibilities. So it becomes more hard to determine what you can expect. So it can be both deterministic or indeterministic. Okay, channel can corrupt the signal statistically. So statistical behavior may change due to the various types of additive and multiplicative noise and fades. So this is what is added to the channel, the noise and the fading. Fading means reducing the strength of the signal. So all these will contribute to what? Change in the signal's property, statistical property will change. So all this leads to error. Finally, the summary here is all this leads to error in data transmission. So today's lecture is more of theory. So we will be talking about some probability. You are transmitting the data with some probability, and at the receiver, what is the probability of receiving that data if there is error? That's the main discussion today. Okay, and all these factors, as we discussed in the previous slide, that leads to, first point is error in the data transmission. That is, you want to transmit a 0, but the channel will introduce some noise, and you get it as 1. That is error, right? You are receiving the data in erroneous way. Second point is that will limit the maximum data rate of the channel. How many bits you can transmit through the channel, that is also will be influenced by the noise. Noise will also dictate that, because you want to transmit 5 symbols, and out of these 5 symbols, 70% of the symbols are affected. That means they are always affected by the influence of noise. So what percentage you can get? Only 30%, there is a guarantee that you will receive the data properly. So maximum data rate, the effective data rate what we can get here, you wanted to transmit 5 bits, but you can only transmit 3 bits. That's also gets affected by channel will also influence that. That is the maximum data rate what you can achieve will be affected by the noise. Okay, then now you'll see some mathematical cases for to study the concept of capacity of a discrete communication channel. So here is a channel, discrete channel. So what is the input to this channel? Some symbols. So M is the set of symbols. The symbols may be ABC or 1, 0 or 1, 2, 3, any symbols, anything. All these symbols are the input to this discrete channel. Now channel has 2 inputs, as I mentioned. I will use my pen here. So there is one more thing I should add here. So what is that? That is noise, right? Noise. N-O-I-S-E. Okay, so now this channel has 2 inputs. One is the input to data, other one is the noise. Because of this, the output here, what you get, it is represented as N. That need not be ABC. Instead, it is something else, A prime, B prime, or C prime. So now all these 3 are the representation of these three symbols. A, when it is transmitted through the channel, because of this noise, it has become A prime. So A prime can be equal to A, or it is something else. B prime, what is B prime? Maybe it is same as B, or it is something else. Because due to the addition of noise, maybe the receiver could receive it properly or decode it properly as B itself, or maybe it was not able to decode properly, so it has represented it as something else, that is B prime, and so on. So anything is possible. We do not know what we are going to get. So in today's lecture, as well as in the next lectures, we will be trying to understand the behavior of this channel. So to study that behavior of the channel, we need to use some probability relations. Then we can get an idea regarding the capacity of the discrete communication channel. Because why do we need to study the capacity? Because when we transmit some data through this channel, there is noise. So overall transmitted information, there is no guarantee that we will receive all of them in the same way, or what the original data transmitted, we will receive the same at the receiver. There is no guarantee. So with the help of these probability relations, we will try to come to a mathematical model. So based on that, we will get the idea what would be the capacity of this channel, or what is the amount of data rate supported by the channel. Whether, for example, why do we talk about data rate? Because you use internet, right? So we say maybe your data rate is, or download capacity is 4 megabits per second, LTE using connection, mobile internet, 4 megabits per second. But originally, what was transmitted? What was the transmission speed? When it was transmitted from the base station, maybe it was transmitted with the 8 megabits per second. Your video, maybe right now what you're listening to the video, maybe it was transmitted at 8 megabits per second. But when it comes through the channel to your phone, due to channel variation, which is a wireless channel, you can get a data rate of how much? Maybe 1 Mbps, or some people who are living far away in rural places, you may be just seeing the screen, right? Maybe not hearing the audio properly, and so on. Maybe you get maybe 500 kbps, kilobits per second, and all that, right? But these, when the telecom companies design their system, they consider all this probability relationship, which is already discussed, and we are studying in your course. You are studying now, but it is a well-known theory. So because of that, they can design the system more efficiently, so that even if you go to some interior place, you should get some minimum data rate. That is what the objective, that is what they will try to design their system as. So this is just, I'm giving a scenario where this model is useful. This model is already defined maybe 50 years before, or even before that. Shannon's or other people have invented this. So now we are just going through that theory. How did they invent all this, and what is their idea, initial idea? And what is the application of this? Application of this study to design any communication system. The best example is maybe telecom communication system, mobile communication system, where data is transmitted at one data rate, one value, maybe 800 kbps, or 1 megabits per second, and so on. But at the receiver, your mobile phone can receive only few kilobits per second, even if it was transmitted megabits per second, right? Why? Because the channel has caused so many issues. But this is not totally unpredictable. There are different theories that have predicted the behavior of the channel. If you want to get at least 100 kbps, then what should be your transmission rate? What I'm talking is here. If you want to get 100 kbps here, what should be your transmission rate here? But we do not know the behavior of the channel, right? Maybe in a city, the behavior of the channel is one type. you are in a very rural place, then the behavior of the channel is something else. Even if that is the case, the theory is made more general. Okay, for a city we have some kind of theories, for a rural place we can have another kind of theories by studying the surrounding components, and we can arrive at a model for this channel. Because due to that we can achieve whatever data rate we want to. Okay, so all that theories, how did they design a communication model, or how did they represent the model of the channel for a city or maybe a rural place? That is what the discussion here. I mean, we are not going to talk in detail about that. I mean, regarding whether how the channel model is designed for a city or how it is designed for a rural place or maybe for an indoor setting, outdoor setting. We are not talking about that in this course, but this course will lay a foundation for all that. Those cases you can discuss in a separate course called as wireless communication. But this course, we will study the background to that. Okay, okay, I continue. The output may be same as the input or different. Told you, when I transmit ABC, what you receive here can be ABC itself, or it can be something else, A prime, B prime, or C prime, and so on, due to error. Okay, now we will come to that probability theory. Because every symbol is emitted with some probability, right? Because this is discrete memoryless source. We have different symbols emitted by the source. For example, a source may emit M symbols, 1 to up to M symbols. These symbols may be just the numbers, or maybe alphabets, or something else. And the probability is represented as Pi of t. I is what? I is the index for all these symbols. Okay, T is what? T represents transmission. You are transmitting maybe 1 or 2 or third symbol, fourth symbol, etc. with some probability, maybe 0.1, 0.2, 0.7, etc. So PIT in general is the probability that the input to the channel is ith symbol. So PIT is the probability of a symbol. There are M symbols. Out of those M, any symbol you consider, ith symbol, its probability. So this is at the transmitter side. So this is the input to the channel. And then Pij is what? It is another probability. This represents another probability. What is this? The ith symbol is received as the jth symbol at the output of the channel. So basically you want to transmit I, but it is received as J at the output of the channel. Then what is the probability? That is Pij. You wanted to transmit A, it is received as B. Then what is the probability? Some value, right? It is 50% of the times it is received as B. Okay, so that is what represented as Pij. So this is at the output of the channel. Basically, maybe I should go back here. Okay, I show you here. PIT is here. You have the channel. To this channel, input is what? Some symbol, PIT. But at the output, what do you get? You may get something else, right? Because of error. So that is Pij, the probability of receiving I as J. I was the transmitted signal, but at the output you get something else, maybe J. So what is the probability that you transmit something, you receive it as something else? What is the probability? Some value, a probability value, maybe 0.2, 0.7, and so on. So that is what Pij is. Pij is a probability that transmitted signal becomes something else. Transmitted signal is I, the received signal is J. What is the probability? Pij. Okay, it's a discrete. I already told you that it's a discrete M-array channel. M-array channel means what? So many number of symbols. There are M symbols here. That's why we call it as M-array. If there are only two symbols, what do we call? Binary, right? Two. B-I-N-A-R-Y, binary. More than two is so many times, m times array, or if it is 3 array, ternary, right, and so on. So maybe 10 symbols. So instead of 10, we call it as in general M array channel. Now, input to the channel is a binary valued discrete random variable X. In this case, if it is a binary instead of M array, what are the possibilities? Either 0 or 1. At the receiver, what should you get? Either you should get 0 or 1 itself. When you transmit 0, you may get it as 0 itself, or you may get it as 1. When you transmit 1, you may get it as 1 itself, or due to error, you may get it as 0. So the output of the channel is also binary. Of course, you know that because only two possibilities. And that is represented by the set y, and the values are 0 or 1. 0 is transmitted, you receive it as 0, or 0 is transmitted, you receive it as 1. That's a wrong reception, error. Next, 1 was transmitted, you receive it as 0, that is error. Or 1 is transmitted and you receive it as 1 itself, that is successful transmission. Okay. Okay, here we will represent all our discussion, what we did so far, as a figure here. So this is what? This is a, all together here, this is a channel, representation of the channel. So this is the input side of the channel, and this is the output side of the channel. We are right now talking about binary, discrete binary channel, or the source. So here we have two symbols. One is 0, other one is 1. If it's a M array channel, you have all those symbols, 0, 1, 2, 3, up to M. Since it's binary, you have 0 and 1, only 2. And you want to transmit 0 through this channel here, and this is the receiver side of the channel. This is the transmitter side here, transmitter side, and here is the receiver side of the channel. I transmit 0 and you get a 0. Then what is the probability representation? P00 or Pij. I transmit I and you receive J. I transmit 0, in this case, you receive 0. Or I transmit 0 and you get 1. How do we write it as? 0, 1. You transmit 0. First symbol here is the transmission. Second symbol here is the reception, what you receive. Okay, and then another possibility, because we have two symbols, right, 0 and 1. So next symbol is 1. I transmit 1 here and you receive it as 0. What's the probability? What's the representation? P10 to denote this probability. Another possibility is I transmit 1 and you get it as 1. What is the probability? P11, right? Maybe in a very good communication system, if the channel is idle, you transmit 0, you should get it as 0. Or you transmit 1, you should get it as 1, right? That's an ideal communication channel. Okay, now we will see a few more notations here. So Pij is what? That's a probability that I is transmitted and J is received. That is equal to probability Y is J, provided X is I. So this is the representation of conditional probability. Conditional probability says if this has occurred, then what is the probability of occurrence of this? Suppose X was transmitted, then what's the probability of occurring of Y? So that's what the meaning here, right? I have transmitted I and you get J. So here X and Y is what? They are the discrete random variables, X and Y. This is for the transmitter and this is for the receiver. Okay. So now we have some relations here. P00 plus P01 is equal to 1. What's the meaning here? 0 is transmitted and 0 is received. That probability. And 0 is transmitted, but it is received as 1. total probability when you sum up is equal to 1. Is it right? See here. We are talking about just one symbol, that is 0. I transmitting 0 and you receive it as 0. Or I transmit 0 and you receive it as 1. The total probability is 1. Is it true? Just like tossing the coin. Because there are only two possibilities, right? When you transmit 0, either it will be received as 0 or it will be received as 1. If 50% of the times it is received as 0, then you know the remaining 50% it is received wrongly as 1, right? I mean, it is a straightforward equation here, right? Similarly, you transmit 1, this is regarding 1, you transmit 1 and you receive it as 1. Or you transmit 1 but you receive it wrongly as 0. Total probability is 1. If 60% of the times you succeed, then 40% of the times you fail. The total probability is 1. Okay. Now, for a few more notations. P of x is equal to 0. The probability of x is the random variable at the transmitter. That is represented as PT0. Okay. So there is a transmitter. You are transmitting 0. And at the transmitter, we have one more symbol, 1, right? So Px equal to 1. That means this value of this random variable is 1 when you are transmitting 1, Pt1. Okay, so these two refers to the transmission side. You are transmitting 0 or you are transmitting 1. You have only two options. Either you can transmit 0 or you can transmit 1. So that is represented this way. The random variable value is 0, when you transmit 0. Random variable value is 1, that means you are transmitting 1. Okay. Then similarly at the receiver, you can receive either 0 or 1. So you are receiving 0, that means PR0. R means receiving or receiver. P is transmission. So PR0. So here P probability of this random variable is equal to 1. That means that is equal to you are receiving the value as 1. So that's at the receiver side. At the receiver side also you have only two options since it is binary. So with these notations we will move forward to find out an important relation here. That is called the error probability. So error probability here is represented as PE. So what is the meaning of error probability? You want to transmit something, but you may receive it as that thing itself or something else, right? So error is when you don't receive it, what you transmit, that is error. You are transmitting X, you are receiving something Y, but they are not equal. You are transmitting 0, you receive it as 1, or you transmit 1, you receive it as 0. In that case, they are not equal, right? X and Y are not equal. That is error. Otherwise, it is not error, successful transmission. So now you're talking about error probability. So in this binary case, how to represent the error probability using those notations? We will see that. So here, probability X is equal to 0, Y is equal to 1. That is, you have transmitted X, but you received 1. That is one case of error, right? What is another case of error? You are transmitting 1, but you are receiving it as 0. Only two cases, right? In case of binary, you transmit 0 and receive it as 1. That is error. You transmit 1, you receive it as 0. That is also an error case. So the sum of these probabilities is nothing but actually the error probability. There is another way of representing this. What is that? Using the conditional probabilities. I mean, this representation is a more involved way of representing this. We are talking about the same thing, but it's a more involved way of representation or more strict way of representing the error probability here. So X is equal to 0. Your input is 0, but you are receiving it as 1. Then what is the probability? That is P of Y is equal to 1 provided X is equal to 0 multiplied by probability of x is equal to 0. That means you are transmitting 0, but here you have the transition probability. That is, you are receiving it as 1. Or, that means you have addition here. You are transmitting 1 multiplied by, you are receiving it as 0. So, we have a strict condition here as well as here. That means we are specifically analyzing if the transmitting symbol is 0, then what's the probability of getting output as 1? In this case, you are transmitting the symbol as 1, then what's the probability that you get a 0 at the output? So this is another way of representing the probability of error. So in general, how to represent this? Probability of the symbol you transmit multiplied by probability of the symbol that you get with error, plus the same for the second symbol. The probability of the second symbol multiplied by the conditional probability. That what's the probability of getting the output in an erroneous way. Okay. So here, probability of what you transmit multiplied by probability of this transition, wrong transition for one symbol, plus probability of transmission of another symbol multiplied by the probability of this transition with the wrong reception. The same lines I'm writing here. Can you understand? So PT0, what is this? PT0 is here. P01, what is that? P01, 0 was transmitted, 1 was received, that is here. Plus, transmission is 1 here. Multiply by P10, here, 1 was transmitted, 0 was received, right? For 0 and 1 cases. Okay, now, at the receiver side, how to represent that? Receiving 0. The probability of receiving 0 is nothing but probability of transmitting 0 multiplied by probability of transmitting 0, receiving 0, plus probability of transmitting 1 multiplied by probability of transmitting 1, receiving 0. It is not confusing. You just see here. What do you want to receive? You want to receive 0, right? So when will you receive 0? Either you will receive 0 correctly or due to error. So what are the two cases? They are here. Either you are transmitting 1 and you are receiving it as 0 due to error. That is what is written here. Or you are transmitting 0 and you are receiving it is also 0. Successful transmission, right? So this is the no error condition. This is error condition to receive 0. At the receiver side, there are only two choices for you to receive 0. Either the transmitter itself had transmitted 0, or transmitter had transmitted 1, but you received it as 0. What are the chances, or what are the probabilities for that? That is equal to here. Transmitter had transmitted originally 0. You received 0. Okay, that case is here. This term or this representation is from this discussion, this general discussion. Plus, you want to receive 0, but actually the transmitter had transmitted 1. So that term. Similarly, you want to receive 1 at the receiver. So what is the probability? Either the transmitter had transmitted 1 or transmitter had transmitted 0, but you received it as 1. So those cases are represented here. You want to receive 1, right? So you want to receive 1. Either the transmitter had transmitted 0, but due to error, it had become P01. 0 had become turned into 1, or I mean plus. That is one chance, one case. Another case is transmitter had transmitted 1, and you received it as 1 itself. There was no slip in the channel. So this is how you represent the error probability. So I think I will stop at this moment.